similar calculations to last time. Calculate the new inductive reactance. Use that to find the third harmonic impedance converted to polar. So we can then use that to calculate the third harmonic current. What is the expression I need to add to my overall expression? Let's just draw this down here. Make it a bit bigger. So what do I need to add to that? To add the third harmonic part of the current to it. .67 sine 300 pi t minus 0.644. Close the brackets. Okay, so finish that off by calculating the fifth harmonic current on the final page. Right, fifth harmonic current, sorry. So XL5 omega 5L 500 pi times 9.55 10 to the minus 3 equals 15. Therefore, Z5 is equal to 12 plus 15J ohms. Converted to polar, that is 19.2 ohms plus shear angle .what? Yeah, and rounded, yeah, correctly rounded, that's still 9 with 2 zeros on the end, isn't it? Yeah. Did you not? I'll do. I'm not overly worried about it. That's fine. Okay. So little I5 is equal to V5 over Z5. It's 30 volts on it, yeah. Comes out as, sorry, 1.56 amps angle minus 0.9. And so the expression to add on to that is, so I'm going to have to put mine down on here, 1.56 sine 500 pi t minus 0.9. Yep. And if I go back to my old friend Desmos and graph, so that's the sine wave with just the third harmonic added. So if we add on, sorry, that's with all three added on. If I add the fifth harmonic current to the blue one, so what was it, 1.56 sine brackets 500 pi x I'm having to use plus 0.9, those brackets should be minus, correct. So you can see that this complex voltage waveform produces a overall complex current waveform, and they aren't overall, they're not in phase either. Okay, so the shape is similar but not exactly the same, and quite clearly the fundamental frequencies aren't in phase with each other. Alright? You're all reasonably happy with that? Then go ahead and see if you can do a similar thing with that circuit. Hang on, oh, I got the wrong one. There's another example. That complex waveform is connected to a 15 ohm resistor, a capacitor of 1000 microfarads, and an inductor of 25 millihenries in series. Calculate an expression for the complex current. Right, where do we start with this one then? XC. We'll call it XC1 if you're doing the fundamental layer, Catherine, yeah? Is equal to? Anyone disagree? Next, somebody different? Ed? Next bit? You might have not done that one first, but what else have you done? XL? 100 pi times 25 times 10 to the minus 3 equals 10.7.85. Yep. There is an argument with that. I got 5/2 pi ohms, and I actually carried that through. So I didn't turn that into a decimal there. I left it at that value. You don't have to, but probably easier, because as you know, as soon as you evaluate pi, you end up with a never-ending decimal or a rounded decimal in your calculator. So sometimes you can make less mistakes by just leaving that as that value. All right. Does anyone disagree with 7.85 ohms for the inductive reactance? Lewis, next bit. Total reactance, yeah, okay. Yeah, that's going to be around 4 point. Is there a way we could do that a little bit more succinct than that, do you think? Can we not do... And you'll have probably got the right answer if you've taken that away from that. So you can do it as R plus XL1 minus XC1 J, can't you? Yeah? And then put the numbers for that in the formula. So that's 15 ohms, right? Plus, and you can write 5/2 pi in there, minus 3.18 in there, J, okay? And you can actually put that in the calculator like that when you do your conversion to polar. So you don't have to calculate the result of this. You can enter that in your calculator by doing the conversion, entering that, putting the comma in, and then putting 5/2 pi minus 3.18 after the comma. You don't have to do that extra step. Right, Lewis? You've still got the right answer. So what answer have you got for the polar impedance?
15.71.
15.71. Yep. Anyone disagree with that? No? Good. So I'll call it Z3 and that should be Z1. Therefore, the current calculated is, yeah, I want the process. Right, under resistor to 10. That nearly came up then, Jack, but I yes, can't agree with that. And the result is average. Hang on, angle of what? Minus 0.302. So the first component of our current is 7 amps sine, oh, the amps don't go in there, 7 sine 100 pi t minus 0.302 amps. So that's the first part. 1 hour. Yeah. All right. You got 3 components here. You'll only get 2 components in the exam because there's no additional assessment really by putting a third one in. Okay, and your calculation is probably going to be around the harmonic resonance situation that we're going to look at next week or the week after, whenever. All right. So there's a bit of this in it, but there's also some addition to the situation that you're going to get in your question. All right. So don't worry, you'll all pass. If you're here every week, that is. Okay. So the second harmonic. Kieran. Where do you start with this one? So we're XL2. And that is, sorry, 5 pi, yeah. Has anyone evaluated that instead? Alright. Robbie, next. One point what? Everyone agree with that? Yep. Caleb, next bit. Yeah, XL and XC we got. Z2. 15. Yeah, so I'll carry on with, so that's 5 pi minus 1.59 j ohms, which converts to polar as yep. Everyone agree? Therefore I3, Catherine, not I3, I2. V3, V2, V2 is 55, isn't it? And the outcome of that, Catherine, is 2.67 radians. So our second component is 2.67 sine 200 pi t minus 0.75 amperes. Amperage. Can't beat them, join them. Right, third harmonic. Do I need to go through this in detail, or should I put my key results up and see if yours are the same? Right. Oh, hang on. What you got for XL3? Because for some reason I got 5 over 2 pi, which can't be right, can it? I'm gonna blame my calculator for the video. Third harmonic. Just the results. Inductive reactance 15 over 2 pi. Capacitive reactance 1.06 ohms. Z3 comes out at 27 ohms, 0.983 volts. Given a current of 0.924 amps angle minus 0.983, and our last component of the current as being 0.924 times 300 pi minus 0.983 radians. So our whole expression if you read out the currents for me, I at T is first harmonic or fundamental. 7, wasn't it? Sine 100 pi T plus 2.67 sine 200 pi T plus 0.924 sine amperes. Mustn't forget the amperes on the end. Alright? So you're gonna get more than likely get a question in the exam that includes elements of what we've done there today, but then a bit more added on to that. Okay? Just as a preamble to what we might do next week or the week after half term. You know you got next week and then you got half term week to follow. Alright? What can you remember about the term resonance? What it means? In particular, we'll be considering series resonance, but we can have parallel resonance too. What can you remember about it, anyone? It would be a circuit that included R, L, and a C component in series. So what can you remember about resonance? We've certainly done something in science, and I thought we touched on it earlier this year, but maybe we didn't. Nobody remember anything about it at all? No. Jog any memory? It's a particular frequency, at resonance frequency, at a particular frequency. Remember, XL is equal to, I'm going to keep to omega L, yeah, and XC is 1 over omega L. So by definition, if frequency goes up, XL is going to get bigger, XC is going to get smaller, and if frequency goes down, the opposite. So there must be a point where those two are equal. Yeah? So their magnitudes are equal. So let's make that 2 ohms. And at a particular frequency, 20 ohms and 20 ohms. Now put that into your formula for impedance of that circuit. Those values. And what do you get? at resonance, the overall impedance of the circuit to that particular frequency is R. At any other frequency, what's going to happen to the overall impedance? If we change the frequency so that the inductive reactance goes up and that comes down, calculate the overall impedance now. We're interested in the magnitude in ohms, so because that's what's going to indicate what the current in amps is. So if we had, for instance, when at resonance, if we've got 100 volts there at resonance, the current flowing 100 over 2, 50 amps. Yep. Now we've changed the frequency, so the inductive reactance has gone up, capacitive reactance has gone down. What's the new impedance? Just quickly, in complex polar form. 20.1 ohms. No, it's about what happens at resonance, Lewis. Right, so the current now is going to be 100, approximately 100 over 20 in magnitude, 5 amps. Yeah. If we go the other way and make this 10 and that one 30, so we reduce the frequency, resistance is still 2, what does the impedance come out as now? Yeah, the same with the opposite angle. Okay, so on either side of resonance, the overall impedance goes down, and therefore the current is much lower. Yeah? So what we can say is, at resonance, qualify that with series. Impedance is at lowest value, and therefore current is highest, and actually it drops off quite quickly either side of resonance. Yeah, so from that 50 amps it will drop away quite quickly. Yeah. Now the other thing is, if we've got this 50 amps at resonance flowing through, I won't worry about angles at the moment, 50 amps through 20 ohms, what voltage does that give us? Magnitude. Worry too much, we're going to do this in more detail. V equals I times R, 50 times 20, 1000 volts across the inductor. Yeah, 1000 volts across the capacitor. The angles of those two are opposite each other. Won't cause any current to flow, right? But those components might not be designed to take that 1000 volts. The capacitor working voltage might not be 1000 volts. The inductor might not be designed to take that 50 amps through its windings that flows at the resonant frequency. So again, we'll do a more detailed example and calculations around that, but it might not be resonance with the fundamental that we have an issue. It might be resonance with a harmonic that's there, but there unintentionally, and we need to talk about where those unintentional harmonics might come from in a circuit. Typical examples. All right, so that'll do us for this week. See you in about half an hour for project. All right.